We're about to start our last subject in engineering math A, which is the last subject of integral vector calculus, and that will be the divergence theorem. Before we can do the divergence theorem, let's quickly review triple integrals because that's how you do the divergence theorem. Triple integral, this is a normal triple integral. This is just a scalar function here, differential volume, integrating over a volume. We have different coordinate systems to do that in. Good old rectangular coordinates, meaning x, y, and z. And you can do this in any order, depending on what's convenient for your problem. And that gives you 6 possible orders of integration. With 2 variables, you only had a choice of 2 ways. Now it's 6. And that's kind of an extra confusion factor with triple integrals. Cylindrical coordinates are basically polar coordinates with the third dimension in the z direction. So x and y are r cosine theta and r sine theta, like before. And the dv becomes r dr d theta dv. Extra r, just like in polar coordinates. And again, any one of 6 orders of integration, depending on what's convenient for your problem. The inner integrals can be functions of the remaining variables. By the time you get to the outer integral, the limits need to be constants. The third coordinate system is spherical. I'm not going to go deeply into this. Theta is this angle in the xy plane, like theta usually is for polar coordinates. B is this angle from the North Pole. It's not quite like Latin 1. But here's what x, y, and z are in those coordinates. Rho is the magnitude or the length of from the origin to the point. Rho squared is x squared plus y squared plus z squared, and dv is this kind of complicated. We would just have this on a formula sheet. You know, I didn't make my students memorize this. So again, you have this complicated dv term, 6 ways to order your variables, and you have to convert your f to whatever your new variables are, your rho, phi, and theta. So that's a quick review of triple integrals, and here's why we need it. The divergence theorem is another way to do certain flux integrals. This is a flux integral. This little circle on the double integrals means it completely encloses a volume. So when your surface totally encloses a volume, you can evaluate the flux integral by evaluating a triple integral, where the integrand is the divergence of the vector field. And the dv is whatever your dv is. Here's another symbolic way to put that. But we're going to have to compute a divergence. We talked about that earlier in differential vector calculus. The convention for what positive flux is out of the enclosed volume. So if you get a negative answer, it means the flux is going into the volume. Here's an example. Find the flux of this vector field, x cubed plus y cubed plus z cubed, and the surface is the sphere of radius a. So what's the divergence? 3x squared plus 3y squared plus 3z squared. This. And it's a sphere, so we'll use spherical coordinates. And this is rho squared. Rho squared equals that part. So all our flux integral becomes this guy. integral of rho squared dv. We're going to use spherical coordinates. This is our dv. And rho squared times another rho squared. Here you go. Look, all the limits are constants, and the integrand can be expressed as a product of the individual variables. So we can, instead of iterating this triple integral, we can make a product of three separate theta part, phi part, and the rho part. And we'll go through those. Those are easy enough to take, get an answer. I'll do one more example in this video. Here's our vector field. It completely surrounds a region bounded by this paraboloid and this plane. I don't know if we've seen this, this looks familiar, but let's see. Integrand, let's take the divergence of this. I have 6xy squared plus 1 minus 6xy squared. Those two guys just cancel, and I end up with a 1. So the integrand is easy enough. So my flux integral becomes this thing. It's just purely triple integral over the body. And in this case, it's going to be best to use cylindrical coordinates. Actually, there's a moral to this example. Taking the divergence is usually the easiest part of the problem. The hard part is the triple integral and doing some three-dimensional thinking. Let's see what we've got here. This surface, z equals x squared plus y squared, is an upward opening paraboloid. This surface, z equals 2y, is a plane. It's not totally drawn here. This is like, if you could just see it looking into the YZ plane, it would just be this line. It actually goes all along the x-axis. That plane slices through the paraboloid. Where do the two surfaces meet? Z equals z, where x squared plus y squared equals 2y. When you convert that to polar, this left side is r squared, this right side is 2r sine theta. So where they meet polar coordinates wise, yes, r equals 2 sine theta. R, kind of have this thing, it's hard to describe. R is going to depend on theta. Let's see. So our dV becomes just the dV for cylindrical coordinates. Just 3 variables extra R. If I do it z first, I'm integrating from the paraboloid up to the plane. So I'm integrating from the paraboloid, which means r squared, or z equals r squared, up to the plane, where z equals 2r sine theta. So those are the limits of the inner integral. I'm going to integrate over z first. I integrate over r first. Here's what's happening. I integrate from the origin out to r. Actually, I don't think I drew this quite right. It should be maximum up the y-axis. That's where sine of theta is maximum. Pi over 2. I kind of squished it down. It should be more stretched out up there. That means r goes from 0 out to 2 sine theta. And then you can see here, theta doesn't really go all the way around. It just goes, doesn't go 260, 360. It just goes pi. 0 over to pi. Here's our setup. Getting those limits right is an important part of the problem. This is the setup. At this point, all we got to do is take a triple integral. I'm not going to go through this pain. And because the limits are not constants, we're going to have to iterate integrals. First, you got to do the inner integral, which will be over z. And there's no z in it, so it's just rz. Where z goes between these two limits. So it's just r times 2r sine theta minus r squared. And you can break that up. Iterate again. These are kind of easy to take. If you take this with respect to r, you'll get a 1/3 r cubed. Evaluate between those limits. Here you get a 1/4 r fourth. Evaluate between the limits. This minus that, and then it's everything's sine to the fourth. At this point, I had to use a table. It's a little tedious, but anyway, we finally got an answer. The important part of that problem, or the part I gave the most credit to, was seeing this. This is the setup. And that's the moral of the story. Usually the easy part is taking the divergence. The hard part, figuring out the triple integral and then actually evaluating it. Doing some of that three-dimensional thinking. After this, I'll do one more example of the divergence theorem, and then I'll wrap up the course, actually, but mostly wrap up integral vector calculus.